So, in the last lecture we began our discussion on aerosol and pointed out how complex the interaction is because of the different sizes of aerosol, different chemical properties and large spatial variation and large temporal variation. Okay? And we are discussing the effect of clouds, and you can see here how as the number of particles of aerosol increase, how the cloud top height can change. The low clouds can decrease and the high clouds can increase. Okay? So, because clouds change the liquid droplets, they tend to reduce the liquid water clouds and increase the ice clouds. Okay? So, fundamentally aerosols suppress the low water clouds and they enhance the high ice water clouds. Now, a long time ago, 30 years ago, Charlson and his collaborators showed that anthropogenic sulfate aerosol, which reflects solar radiation, has imposed a major forcing comparable to greenhouse gas, but opposite in sign. Greenhouse gases warm the earth's surface. Sulfate aerosol cools the surface, and they claim that the impact of sulfate aerosol was as large as the impact of greenhouse gases. Till that time, people did not realize the impact of aerosols on Earth's climate. Now, the challenge we face is carbon dioxide is continuously increasing in the Earth's atmosphere on account of the burning of coal, oil and gas. But sulfate aerosol, which were increasing along with carbon dioxide till recently, has started decreasing in some parts of the world, but is increasing in Asia. Now, why is sulfur dioxide emission decreasing? It's because of our concern with air pollution. I told you that the biggest impact of aerosol is on our health, because we inhale these particles, small particles, which goes deep into the lungs and affects the lungs substantially. Okay? Causes various allergic reactions and also various diseases. Okay? Because of that, in the developed countries, they have already cut down the emission of sulfate aerosol. But this has not happened in China and India yet, but it is bound to happen, because people are going to realize that the impact of aerosol on health is immediate and we need to take action if we want to improve our health. Now, here is an estimate by different groups of the amount of sulfur dioxide emission in gigagrams. Okay? You can see there is a lot of variation. One shows that the sulfate emission peaked in Europe around 1970 and it started declining rapidly. And same is true for North America. North America and Europe both have enforced strict air pollution control laws around 1970, and that declined the amount of SO2 emission. But in Asia, India and other developing countries, it is continuing to increase, because we have given lower priority to SO2 emission than the developed world. Okay? We have not realized the serious consequence of emitting sulfate aerosol, and so we have delayed. But what the work of so here is another estimate made in 2009 of the emission of sulfur dioxide, nitrous oxide and soot emissions. Okay? So, you can see that some of the more recent estimates claim that the soot emission is declining. And as the people in the developing world recognize the consequence of aerosol on human health, we believe that decrease is not occurring everywhere. So here is an estimate of aerosol emission as given by Arvold and Data, and you see that the peak emission of sulfate emission occurred around 1995. Okay. After that it has slowed down mainly because of low reduction in Africa and China, but aerosol is still increasing in India and China, but overall it is declining. Okay. This is good news, but India and China are still going up. Now, if you look at the black carbon emission, again I want to remind you the sulfate emission is typically 120 million tons, okay, while that of black carbon is much lower, okay, about a tenth. So the annual black carbon emission in teragram is less than 10 teragrams, okay, but there is a large variation you can see. Different groups are estimating the amount of emission of aerosols by sulfur combustion, and it has a wide range here, factor of 1.5 to 2. And if you look at black carbon emissions, it is much lower than sulfate, but still over Asia the concern is it is going up too rapidly. Okay. It is going up very rapidly in Asia, and so that is concern should be first for health and then for climate. Now here is the annual emission of SO2, black carbon and sulfur and organic carbon given by 2020. Yeah, so there are different models. I want you to notice that different models show different levels of concentration of sulfur dioxide, black carbon and organic carbon. Now here is a measurement of the aerosol optical depth from satellite, okay, and what you see here is there is a signal cycle in different parts of the world, and these are measured from two NASA satellites, Aqua and Terra, sampling the every 2 hours. And what I want you to remember in this figure is that aerosol emission over India is very high throughout the year, and in contrast the aerosol emission in Australia is very small. Australia has very strict air pollution control laws, so they do not allow. Now the reason why aerosol optical depth is small over Australia is because the population density is very low in Australia, so the industrial emissions are limited, while India and Southeast Asia have high aerosol optical depth because of high population density and lot of industrial emissions. In Sahara, the main reason is natural, which is coming from high winds over Sahara, which kick up dust in the atmosphere into very high depths. Now here is a picture showing the variations in the composition of aerosols around the world. There is a sample from India, sample from China, sample from Europe, sample from North America, eastern region and western region, and of course Africa. Okay. So, the first glance I want you to notice there is a large variation in the composition around the world. Africa is mostly biological in origin, okay, because it is not much industrialized. You look at the Pacific Ocean, mainly sea salt aerosols. You look at eastern North America, the major emission is sulfate from industries. Europe also mainly sulfate, and China also mainly sulfate. Okay. India has mineral as well as sulfate, and both India and China have black carbon aerosols which are not that prominent in the developed world. So, this is a problem when you want to model aerosols. You have to take into account the changes in the chemical composition which varies with location, and these observations began only around 20 years ago in India. So, we do not have sufficient data for modeling. The other thing this data shows from models is the black carbon aerosol, which is very high in the month of January to March, declines in the monsoon season and picks up again in the winter. While the monsoon season, dust is dominant. So, in the pre-monsoon and post-monsoon, black carbon dominates. During the monsoon, the wind kick up dust. Now, here is an estimate made under the US climate change program of the global source of sulfate, black carbon, particulate organic matter, POM, dust and sea salt. And I want to notice that the highest is sea salt, 6000 teragram, next is dust, 1600, next is sulfate, 190 teragram, and then particulate organic matter, 100 teragram, and then black carbon, which is only 11 teragram. So, remember that black carbon emission is about a 1/20th of that of sulfate. So, I will point out why this is relevant a little later. Okay. And so, in the atmosphere, for example, this is the emission. Atmosphere, there is 2 teragram of sulfate, only 0.2 teragram of black carbon, it is 1/10. Okay. And the lifetime is all around 4 to 6 days, not very different. And optical death varies between 0.03 BC is very small because the emission is small. And here is the estimate in milligram per meter squared of sulfate, black carbon, and the sulfate is measured in milligram per centimeter squared. Here it is a percentage contribution with respect to 80,000. How much is the percentage contribution? Okay. And you can see again that if you see the scale here, the sulfate burden is much larger than that of black carbon. Okay. The colors show up to 1 milligram per meter squared, while black carbon is 0.1, 0.2 milligram per meter squared. Okay. Now, if you look at the emission sources on the left in grams per meter squared per year, on the right percentage anthropogenic contribution, you can see over most of the land, especially highly populated regions of Eastern North America, Europe, India and China, most of the emission is anthropogenic, almost 100% human. while in areas with less population density like Africa and South America, it is somewhat lower. Okay. So, places like Amazon, major source will be natural, not man-made. So, because of this aerosol, there is more radiation reflected by this aerosol to space. So, a negative atmospheric force in watts per meter squared, and the value is around 0.5 watts per meter squared, negative value indicating reflection of solar radiation. Now, aerosols affect climate two ways. Salt and sulphate reflect solar radiation, so they cool the atmosphere and the surface, while dust and soot heat the atmosphere because they are absorbing, but cool the surface. So, this diversity affects the impact of aerosols on Earth's climate. So, the aerosol properties depends on the mixing state, because aerosols are released individually as soot or sulphate or salt, but when they go in the atmosphere they start mixing. Okay. So, the mixing state is very important. Imagine a dust aerosol is surrounded by salt, then its absorption will not be seen. On the other hand, if soot coats sulphate or salt aerosol, it will fundamentally alter the properties of that aerosol. So, this is one of the toughest challenges we face. We have very little data on the mixing state of the aerosol, because you actually go there and grab the aerosol and look at the mixing state. It is a very tough situation. And here is a cartoon showing what is called external mixing. The black carbon and sulphate or salt are separated. Here black carbon is inside, coated by sulphate, and here is completely mixed. Internal mixture means they are all uniformly mixed, so it gets a grey color. This looks white, this is distinct, they don't mix. Here salt or sulphate coats on black carbon, so it looks white. Here they uniformly mixed, they look grey. So, that is the difference in the forcing in watts per meter squared, because by the mixing of aerosol. Now, recently there was a concern about how aerosol will affect the Arctic sea ice. It is melting rapidly, we talked about it. So, the rate of melting of Arctic sea ice depends upon both global warming by carbon dioxide and the deposition of soot on the sea ice. Okay. So, this has been a major concern, that in the Arctic the black carbon on snow will have a huge impact compared to the global average. Okay. So, this black carbon released from Australia, Canada and America will blow into the Arctic Ocean, which has sea ice on it, and it will deposit directly on the ice, so will melt it very rapidly. So, much of the Arctic warming, Schindel and Falvugi tell us, is unintended consequence of clean air policies that have greatly decreased the sulphate aerosol. See, if sulphate deposits on ice, it will not have too much effect. It is also reflecting, ice is reflecting. But if you remove all the sulphate by strict air quality standards, then black carbon and carbon dioxide will cause the melting of the Arctic sea ice. So, that is the point they are making, that sometimes air pollution control can have a different impact on Earth's climate, because it removes the reflecting aerosols. Now, when you come to India, here is a photograph of the Gangotri glacier, one of the biggest glaciers in Himalayas. Behind is the Bhagirathi peak, and this glacier you would think would be white in color because of ice and snow, but no, they are covered with rock and dust from the surrounding mountains, so they are brown in color. So if black carbon or other aerosols which are absorbing fall on the Gangotri glacier, it will not alter the albedo too much because it's already dark. But Arctic ice is different. Arctic ice is extremely white in color, so there the impact is dramatic. Here the impact will be limited. So people have studied the impact of greenhouse gases, volcanic forcing and black carbon. They are saying that although people are concerned about the effect of black carbon, they don't see much effect on temperature when compared to greenhouse gas and volcanic forcing. So regarding black carbon, there is a lot of controversy, and I will talk about that a little later. So UNEP, United Nations Environment Programme, put out a document saying that by controlling air quality, we can control both air pollution as well as the global warming. But this turned out to be wrong, because if you control air pollution, especially sulfate aerosol, which is reflecting, it will increase the impact of greenhouse gases. Right now the global warming is somewhat lower than what it should have been due to carbon dioxide, because sulfate aerosols are reflecting sun's radiation. If you remove all the sulfate aerosols, you will get much higher warming. So there was a confusion caused by IPCC about 10 years ago by calling aerosols and methane as short-lived climate forces. Now this was done because both these things had a much shorter lifetime than carbon dioxide. Okay? But methane aerosols are very different. Aerosols have a lifetime of weeks, methane has a lifetime of 10 years. Aerosols chemistry is simple, it converts from methane to carbon dioxide, while chemistry of aerosols is complicated, depends upon it is sulfate or black carbon or something else, okay, or organic carbon. Aerosols can cause warming or cooling depending on the composition, while sulfate only causes, methane causes only warming. So it was not a good idea to combine these two, but it was done for a certain political reason, which I will talk about a little later. Now the recent IPCC report, the sixth assessment which came out recently, has clearly shown the difference between what happens with greenhouse gases here. If you reduce them, you get a benefit. If you reduce black carbon, warming will come down, the health benefit also will go up. Same thing with ozone at the surface. All the three, if you reduce, but if you reduce sulfate or organic carbon, which reflects radiation, it will warm the Earth's atmosphere but improve air quality. So sulfate is one thing which, if you reduce, you improve air quality and cause global warming. So this is a point now which is of great concern. Now on the right I have shown how this assessment shows that the major impact of aerosol is not the direct impact through absorption scattering, but indirect through clouds, and it is much larger than direct, and unfortunately there is a large level of uncertainty. So this is a major issue that we have to deal with, that the aerosol cloud interaction is very complicated. Different models do not agree about the magnitude of the impact. Okay. So, the large uncertainty shown right here, all the way from 0.5 to minus 0.5 to minus 2 watts per meter square. Now, here is an example of how the aerosol optical depth has changed according to the different CMIP6 models used by IPCC. Okay. So, you can see whole range saying that they have contributed 0.02 to optical depth to 0.08, a factor of 4 times, okay, with the mean value being around 0.04. So, this is a huge issue. The range is so large that it causes a large uncertainty in our predicting the impact on climate. Okay. The net effect is, of course, is cooling, that we all know. So, black carbon is not having the kind of impact people thought 20 years ago that it may have. So, it is mostly cooling most of the areas, especially where the aerosols are large like China, India and North America. Now, you can see that the aerosol impact, if you take the total, it is total is here global mean black. So, it is increasing by the sulphate increase, but in the last 20 years sulphate aerosol has declined, and so the impact of solar aerosol is reducing. So, very soon the impact of aerosol may be close to 0. Okay. So, it will not, so far aerosols were causing cooling, CO2 was causing warming, and the combination has somewhat mitigated global warming, but that will not happen in the future. Okay. You can see surface temperature decreasing in most parts of the world due to aerosols. Okay. Now, the recent report also shows that it also has a impact on the ocean, okay, because it causes a change in temperature within the ocean. Okay. So, southern Indian Ocean, where there is not much land, is showing below the thermocline changes due to aerosol induced heating. Okay. Now, here are a few examples from India. India, a lot of work has been done on aerosols because of concerns about both air pollution and climate, and there is a steady increase around 2% per year from 85 to for about 30 years. Data shows increase from various stations all over India, and the highest levels of course are over the Indo-Gangetic plain. Okay. That is shown by the satellite data showing a huge aerosol loading coming into the Bay of Bengal. And here is another example of the increase in aerosol optical depth, and measurements were made of aerosols vertical variation, which is important for simulation of the impact of aerosol, and it was found that aerosols maximum amount is not at the surface, but at about 4 kilometer height. So, this was a great surprise, and the exact reason for this is not clear, although aviation may be playing a role. Okay. So, this is a concern that has emerged recently of the role of aircraft on Earth's climate. Okay. Here is an example from balloon launch from Hyderabad showing that the temperature gradient in the atmosphere has been altered where there is a lot of aerosols. So, this is a new result which has to be looked at very closely. Okay. And these are called elevated aerosol layers, which have an impact on the temperature variation with altitude. Okay. But still, if you look at the emission inventory of India, sulphate emission is still much larger than black carbon. Okay. So, black carbon emission is large in India, but still smaller than sulphate. And you can see that in the developed world, both East Asia and India, the aerosols were increasing, but in the last couple of years it started decreasing. Okay? And the SO2 is increasing and SO2 has decreased, black carbon is still increasing. Okay, I will stop here with a mention about why aerosol became controversial, because in 2001 America decided to withdraw from the Kyoto Protocol on greenhouse gases, saying that black soot contributes to warming. We know today that was a false statement. Today we know that black soot impact is very limited, and this particular excuse given by United States was not valid. We will discuss this more in the next lecture.